All right. All right, can you still see my screen?
Yes.
Yes. All right, great. Yeah, so thank you everybody for coming. Today we're going to be talking about my PhD dissertation work, emergence via constraint optimization, analysis and experiments with constraint-driven flocking. Oh, thanks, Ish. So the first thing we need to talk about is, what do I mean when I'm saying we're studying emergence problems? Really what we're looking at are large systems consisting of many simple individuals that are interacting locally with their neighbors. For example, the way these bees are interacting with their neighbors, and they're forming some system level organization, some sort of organization that's larger in time and larger in space than the individual agents and their interactions. Again, like you can see maybe in a flock of starlings, forming these long organized patterns that are bigger than any individual agent in the system. And really the question we want to answer is, how can we engineer emergence into our engineering systems we're looking at? And this is a pretty poorly defined topic. What is emergence in these multi-agent systems? And so the definition we're going to go with is provided by the cybernetician W. Ross Ashby. And he claimed that any system with multiple interacting agents that have a local feedback control law, and where the system goes to some set of equilibrium points, we can qualify that as a complex system. So in this case, we say that a system going to equilibrium is the same as some global organization emerging. You can imagine no matter where you stick these orange balls initially, they'll converge to some equilibrium point. And this is the emergence of large-scale organization from these local interactions acting on each part. And this leads to some interesting properties that Ashby points out. One is that most emergence is bad, or at least not useful. It's just a system going to equilibrium. And if we want to find an equilibrium configuration that's actually useful for an engineering problem, we're going to have to go out and find it. And in fact, we really need to define ahead of time what we even mean by good. And these are all very useful questions we can answer from sort of a controls perspective. Of course, this isn't just an academic exercise. The control of multi-agent and multi-robot systems is important to European robotics, US robotics. It was named one of the grand challenges of science robotics. And it's also pretty closely related to some of the NSF and UN's sort of big ideas and large problems they're trying to solve. So we're going to talk about three different parts to this presentation. In the first, I'm going to go over sort of how we can merge complexity and multi-agent systems in what I'm calling the medium complexity problem that Ashby proposed. We're then going to get into more concrete examples with constraint-driven flocking. And finally, I'm going to discuss how we can actually put these control algorithms on physical robots out in the environment, because we need to do optimal control very quickly before we're able to do real-time control with this. So the first problem I'd like to talk about is this idea of a medium complexity problem. When you look at this equilibrium definition of emergence, if you only have one or two equilibrium points, the problem becomes sort of trivially simple. You can just sort of abstract things away. It's very intuitive. But if you have a biological system, you may have hundreds of thousands or millions of equilibrium points, and you sort of get lost. It's very hard to analyze. So what we want to find is a problem that's somewhere in the middle. You may not be able to guess exactly what the outcome is going to be, but we're able to analyze it. We're able to simulate it on a computer. And this problem is goal assignment. The idea is we want to take n agents and assign them to n goals. For example, if we have a drone light show, we want the drones to move into formation and track these points in 3D space. And it's decentralized control. So in this case, each drone is going to be making its own decisions at every time step. We have local feedback because the agents are going to be looking around at their neighbors before they're deciding which goal to assign themselves to. And we have a very large feasible space. We can start with essentially an arbitrary assignment of agents, and we're guaranteed to converge down to a feasible assignment where we have one drone assigned to one goal for every drone to go to. And there's a lot of related work. This is a really rich area, this formation control stuff. In fact, you can see even every 2 years, it seems, they're publishing new survey papers on new methods to formation control. And the particular contributions of this section, first, we have an energy-aware assignment algorithm. A lot of existing work just uses things like a minimum distance metric, which doesn't work as well to save energy when you're in a dynamic environment. We also have very weak requirements for convergence in finite time to the goals. A lot of existing work requires special spacing between goals or requires some initial knowledge of where all the drones in the system are located. And then, of course, because of both of these, we're able to improve energy consumption. So the first thing we need to talk about is the feedback mechanism. How is our system actually evolving with time? And what we're really interested in is how we're assigning these agents, which are these circles here on the right. We care specifically about this green agent. And we want to have some sort of local interaction and local feedback between the agents. So in this case, we're going to define a neighborhood. So this green agent will be able to communicate and sense all of these orange agents around it. And this is the information they're going to use in order to actually solve their assignment problem. The green agent in this example is going to assign itself and all of its neighbors to the set of goals that minimize the energy consumption of the entire neighborhood. So it's going to get a different assignment than as if it were selfishly solving it, and also a different assignment compared to if you have some global solution that assigns all the goals simultaneously. This green agent is then going to select the goal assigned to itself, and this is how it's going to pick its desired goal. And this is going to happen because it's decentralized. Simultaneously, every agent is going to go through this process. So we may have this orange agent to the right assign itself and its two neighbors to these three goals, because that's the information it has, that's the assignment that it ends up with. And we've encountered sort of an interesting problem now. We have two agents in the same neighborhood assigned to the same goal. So we're not actually going to be able to calculate a feasible trajectory because the agents are going to collide when they both try to arrive at this goal. So what we do is we institute some sort of banning mechanism. We can have some heuristics, such as looking at the neighborhood size of the agents to determine who has more information, looking at the energy cost of reaching the goals. And one of the two agents is going to sort of win this comparison. That agent will be assigned to the goal. The other agent will be permanently banned and have to select a new target. And so in this way, we can push all the agents to the goals after they do their initial assignment. They may have to reassign themselves and perform the banning process again if they come into conflict, but eventually they're going to arrive at all of their goals. And these are actually the results we got. So you can imagine if you have enough unbanned goals that you can assign all the agents to goals. And it turns out using an event-triggered assignment scheme is sufficient to have enough goals. If I assign myself to a goal, I will remain assigned to that goal until I have a conflict with another agent that's entered my sensing radius. In that case, you'll figure out which agent is banned. One agent will remain assigned to that goal, and the other agent will have to redo the assignment. And when you guarantee that enough goals exist, you can show that the assignment matrix will converge in finite time. So we've shown that we're satisfying all these properties of complexity. We start with an initial assignment, we converge to a feasible assignment, and in fact, we're doing that convergence in finite time, which has a lot of value from an engineering perspective. Now, I also mentioned that we're saving energy. One of the problems with dynamically redoing the assignment is your agent's not always going to start with zero speed, and your goals are not always going to have zero relative speed. So you can imagine a case where this agent is sort of moving towards the goals, and the goals are maybe moving relative to each other. And we want to try and estimate about how much energy is it going to take for the agent to go to these three goals, because we want to minimize the energy consumption of this agent and its neighborhood. So under the dynamics we used here, we've got just integrator dynamics, and we're minimizing the control input. We get a optimal trajectory that looks like it's linear in acceleration, it's cubic in position, and it has these constants of integration, A, B, C, D, which come from the initial position and state of the agent and the final state of the goal that it's approaching. So you can imagine these trajectories will look something like this, that the agent will follow. And in fact, we can calculate explicitly what the energy cost is for this agent to reach one of the goals in finite time. And it's just a function of how much time is remaining in the system and these coefficients. So we can actually go through and for each agent, calculate the cost that it would take for that agent to arrive at any goal in finite time. And we use that as the cost in our assignment and as the cost for our tiebreaker. And you can see this functioning on the left. We have some agents that start off. You can see their neighborhoods marked by this dashed circle. They initially go towards sort of the closest goal because that's the easiest to get to. As they interact with each other, they'll spread out and move to separate goals until they've converged. We can do the same thing here on the right with a dynamic system where all the goals are moving up and to the right, and they're also moving relative to each other. They also have a fixed sensing distance here. I've just hidden it to make it easier to see what's going on. And you'll see again, the agents are encountering each other, updating their information, converging to goals. And we get this sort of interesting searching behavior where the final agent in the system needs to gather more information to determine what goal is available. And you can see we get, again, this finite time convergence. And so you can see here, this is what the problem looks like in the centralized case where we have all the agents going to their assigned goals. And so we've sort of showed how we can look at emergent behavior. In this case, these agents sort of spreading out and searching for goals is just the convergence of a matrix to some final value. And also how this emergent behavior has given us a nice finite time guarantee on the behavior of the agents. And in addition to that, we think we found a pretty good equilibrium because we've been able to reduce the energy cost of the system relative to just looking at the distance to the goal, for example. So this was sort of a warm-up for the next section here. We're going to talk about
Logan, just a quick question. So in the previous results, do you have some kind of minimum separation distance for concurrent flight, or?
Can you repeat the question?
Oh, yeah, sure. So the question is, do we have some sort of minimum separation distance for concurrent flight? In this work, we didn't consider a minimum separation distance between the agents. And part of that was because it was very slow to calculate the entire constrained trajectory. But we can talk about that more in sort of the third part as well. Okay. It's also going to make things more difficult with the assignment because it's going to not only depend on where an agent is assigning itself, but if it comes into any conflicts with its path.
Okay, very good. Thank you.
Great. So yeah, in the next section, we're going to talk about constraint-driven flocking, where instead of looking at an assignment matrix being optimized, we're going to have the agents explicitly minimize their energy consumption. And we're going to try and drive the system into an energy favorable configuration. But first, we need to be clear on what I mean by flocking, because this is really an ambiguous term. In fact, there was a recent paper published in sort of the biology literature saying we should really use cluster flocking. That's like swarming behavior like starlings or sparrows or pigeons. And we should use line flocking to describe what geese do in these long, mostly steady lines and V shapes. And we can borrow that terminology and also apply it to the engineering literature. So you can imagine if you have a certain application, such as tracking a ground vehicle, you may have a flock of agents sort of swarming over the top of it. Whereas if your goal is to try and minimize energy consumption, you're more likely to see one of these steady sort of line formations. And so one of the things we've done is we've sort of classified cluster flocking based on different applications that we found in the literature, and you can classify line flocking based on the different environmental effects that actually affect your energy consumption. And so the problem we're going to be looking at is the emergence of line flocking. So we have a bunch of agents that are minimizing their energy consumption, and we know they're going to converge to an equilibrium point because that's how we're going to design the controller. And so we can get the entire system into one of these energy saving configurations, such as a V of geese or a platoon of vehicles. And this is also a pretty popular problem. It's fairly closely related to convex optimal control policies, which Stephen Boyd at Stanford discusses a lot, where instead of using like PID feedback control, You solve an optimization problem at each time step in order to generate your control action. It's also very similar to ecologically inspired robotics, although I'll highlight a couple of differences as we're going through the different formulations and results. And it's also fairly closely related to control barrier functions and saturation functions, because this is a set theoretic method where we want to guarantee constraints. And so some of the results from control barrier functions can be used to implement what I'm about to show you. In terms of contributions, we have a few here. The first is I'm going to show you how we can get guarantees on the behavior of the system just from looking at pairwise states between agents. I'll also show you how this is sort of a data-driven control technique without using black box methods you may find in machine learning. I also will show you an equivalent sort of finite state machine formulation, which makes everything very easy to interpret, because by checking the finite state, you understand why an agent is taking a particular action. And then, of course, we'll finish off with the emergent V formation, which comes from agents trying to just minimize their energy consumption. So to start, what is constraint-driven control? Say we have this blue agent I in the upper left, and we want to reach some sort of objective, which is this X in the bottom right. You may be tempted to take the error in the agent's position and use some sort of PID or stabilizing control to drive the agent there, but we're constraint driven. So instead, we're going to impose a constraint, such as the dot product of your velocity in the direction of this goal must be non-negative. So we have this conic motion constraint that's going to pull our agent towards the X. We also may need to avoid some obstacles. So we can add in a collision avoidance constraint with another obstacle. And once we've defined our set of feasible actions, we will then have to define our objective function, which determines how the agent actually moves through the space. And this is going to be critical, as we'll see later, to determining what the system level behavior actually looks like. Once we have all of these things defined, the last thing we need to prove is recursive feasibility. The idea that if I take a control action now, I want to be able to take control actions forever after that. So for example, if this agent were to drive directly at this obstacle at a high speed, for a while, it would be taking feasible control actions until eventually it will get into a situation where no matter how hard it brakes, it's guaranteed to collide. In that case, we've broken recursive feasibility. So we want to avoid that situation. So the first example we'll look at is this idea of platooning on a highway. We're going to have a vehicle I, and we'll have some vehicle indexed to I-1, which is in front of us. We're going to consider just the longitudinal dynamics on the highway. So we're going to control the acceleration of the vehicle directly. We'll assume the vehicle is able to sense the position of the vehicle in front of it. Note that this is a negative vector. It just makes taking some of the derivatives easier. In addition, we're going to try and minimize the acceleration squared, or the control input squared, because we want to minimize sort of our transient energy operation. In addition, this will give us some very useful results at the end for how our system behaves. Of course, we also have a safety constraint. We want to maintain some distance delta from the vehicle in front of us so that we don't rear end into them. That would be could be disastrous. And so far, we've got kind of an interesting constraint-driven problem, but what really makes it line flocking is if we also look at the aerodynamic interactions between the vehicles. So if I'm vehicle I know that there's a low pressure bubble behind the vehicle in front of me that I want to move into and take advantage of that to reduce my drag force. And so the first thing we need to do is we need to ensure recursive feasibility. We want to make sure our vehicle is always able to take another control action so we don't have an accident, for example. So imagine if vehicle I is following vehicle I-1 at an unsafe distance. Maybe it's moving much faster than it. It's much closer to the vehicle in front of it than it should be. It turns out just having this safe stopping distance isn't enough. The front vehicle may suddenly slam on its brakes if there's a pedestrian or something else in the road, and you're going to end up with a rear end collision sometime in the future. The way we can mitigate this is by augmenting this with some sort of stopping distance. So we want to maintain our fixed distance plus however much distance is required for us to stop. So we can see that in this constraint here. We have G just symbolizing the constraint for vehicle I's rear end safety. So if we're moving slower than the vehicle in front of us, our original constraint is sufficient because the vehicle in front of us at the next time instant is going to be further away. So we're at no risk of rear ending them. However, If we're moving slower than the vehicle in front of us, then in this case, we need to add in or if we're moving faster than the vehicle in front of us, we need to add in some extra terms that capture the difference in the vehicle's velocities, as well as our velocity and acceleration constraints. So with this augmented form, we can guarantee if the vehicle in front of us slams on the brakes, we can also slam on the brakes, and we'll always have this safety guarantee. So we've proved one safe control action always exists: slam on the brakes, and we satisfied recursive feasibility. The next thing we can look at is how the drag minimization plays into all of this. So here, where we want the derivative of the drag force squared to be non-increasing. So the idea is the vehicle will never take an action that causes its drag force to go up, because that would cause its fuel consumption to go up as well. And so we can take the full derivative here. This is just the definition of the time derivative. And we know that as our speed increases, our drag force is going to go up. That's just coming from aerodynamics. In addition, as we get closer to the vehicle in front of us, as this negative p hat gets more positive, our drag force is going to decrease because we're moving into this low pressure wake. So, oh yeah, Sam, go ahead.
I have a question. So why did you choose drag to minimize instead of something like acceleration, which also is related to fuel?
Sure. So the question is, why minimize drag and not something like acceleration for the people on Zoom? So we're actually minimizing the acceleration in the objective function, and we're minimizing the drag force as a constraint. So we're sort of minimizing both in a way, but we're being more strict about minimizing drag.
Why?
If we minimized acceleration as a constraint, it would be too restrictive, because we'd have to have, basically we'd be bringing our acceleration limits in to be like very tight, right? If we want to minimize acceleration. We could also put the drag force in the objective function with the acceleration as well. But you actually get very interesting sort of behavior when you include the drag as a constraint instead, if that makes sense.
So you said you can switch, right?
Yeah, you could switch. It's just the behavior of the vehicle would change.
In what way?
So in this case, we're forcing the drag to be minimized. So that means that, and let me show the next equation here. So we actually have this requirement on our acceleration when we rearrange this equation. And so if we're moving slower than the vehicle in front of us, this will be negative, and we have to actually decelerate. Whereas if this was in the objective function, we may be able to temporarily increase our drag force. It would be almost like less strictly greedy. But then it would be much harder to make claims about how the system behaves, because you've got a bunch of terms in the objective function instead of as constraints on the system.
So is it for ease of, I guess, solving, or is it because you'll have like safety, like what?
Yeah, so the idea is the constraints give you guarantees on how the vehicle is going to behave. Whereas if they're in the objective and they're weighted, you don't have as good of guarantees.
Okay.
And so we can actually use this guarantee that our acceleration can only increase if the vehicle in front of us is moving faster, to describe how the whole system behaves based on sort of the local rule applied on each vehicle. So that's sort of the benefit of having everything in as constraints, even though it may make solving it a little bit more challenging, as opposed to if we maybe put this in the objective function and we like minimize drag plus acceleration squared or something.
So would you say this is like a safer approach?
I don't know if it's necessarily safer, because in both cases you would have, you would still have the same safety constraint. So I don't think it's necessarily safer. Yeah, I guess really it's just because this tells us how the platoons are going to behave is the reason it's useful to have it as a constraint. Otherwise, we could have put this in the objective instead, but then we're just going to know that, we want to get as close as possible maybe to this acceleration, which is positive or negative, instead of trying to minimize acceleration in the objective.
Thanks.
So great. So in this case, I guess this also may answer the question a little bit more. This is effectively a data-driven control technique because our vehicle I is selecting the maximum acceleration it can have using information about the vehicle in front of it. That's this VI hat. And also by using information about the derivative of the drag forces, which you can imagine if you have some type of drag sensor or some sort of aerodynamic model, you're essentially changing the bounds of your feasible set by looking at these measurements, and then you're taking that in as a constraint on your system. And so this is the optimal control problem that we end up with. Each vehicle independently is going to minimize its acceleration squared to minimize the transient energy operation. We have this set script AIS. This is the set of safe actions for agent A. And this includes minimum speed, minimum and maximum control input, as well as our safe following distance. So we know that this set A satisfies recursive feasibility. In addition, we have this drag reducing constraint, or maybe drag maintaining constraint, where we want this, we upper bound our control input to ensure that our drag force does not increase. And finally, because we're minimizing the acceleration squared, this is going to help us understand how the system is going to behave, because we know vehicles are going to pick the smallest accelerations possible, subject to this constraint. But before we get into that, there is one more issue with this control policy we need to talk about, and that's the idea of constraint compatibility. So we've shown that our safe action set satisfies recursive feasibility. We can always pick another safe action. The problem is that is occasionally incompatible with our drag constraint. For example, if we're moving at the minimum speed, our only safe action is don't accelerate or speed up. But if we are moving slower than the vehicle in front of us, then we know that our only drag satisfying constraint is to slow down. So although both sets have feasible control actions, when we take their intersection, it's an empty set. And we can say the same thing about the acceleration limits. Now, the way that this is handled in a lot of other approaches, especially ecologically inspired robotics, is they'll basically do exactly what Dr. Doss has suggested. You maybe move the drag force into the objective function, you maybe have a penalty function, and you allow this constraint to become relaxed. Instead, we've come up with a finite state machine approach, where you have a finite state machine that describes what type of behavior the agent is showing. So everything we've talked about so far, we can classify as a platoon follower constraint. The vehicle's trying to minimize the drag force, it's trying to, not rear end the vehicle in front of it. But if these conditions, 27 and 28, either of them hold, we know the feasible set's empty. So the vehicle may transition to becoming a platoon leader. In this case, we can relax the drag constraint, and you can imagine having several platoon leaders in a system communicating and coordinating with each other. But critically, this may lead to all vehicles in the system eventually becoming platoon leaders, and we won't have any actual platoons formed. If 27 and 28 are no longer satisfied so that we have a feasible action space, we force the platoon leader back to becoming a platoon follower. And this also allows the system to deal with things like vehicles entering on an on-ramp or exiting, because as the data it's receiving about other vehicles in the system changes, it may change its behavior back to being a platoon follower. And so with this formulation, we can now be happy that we've satisfied recursive feasibility for all the vehicles, whether these conditions hold or not. The last thing to talk about is how we actually get this system level behavior out of the vehicles. So here you can see we've got our minimum and maximum acceleration. We're minimizing the L2 norm of acceleration here. And our only lower bound we may have is if we're at the minimum speed, our acceleration should be 0 or greater. So we know that our lower bound is either a min or 0, and the rest of our constraints are actually upper bounds on the problem, right? We may have some safe distance we need to maintain, so we can't accelerate too much. We may need to reduce our drag force. That could be a different upper bound that further reduces our maximum acceleration. But really the point of this is we know the lower bound of this acceleration is non-positive. And what that means is whatever vehicle's in front of us, it's never going to accelerate in this case. Because if the vehicle in front of us accelerates, well, that means it could have taken 0 as a control action instead, because our upper bound is obviously positive and our lower bound is at least 0. So in this case, we can actually talk about how the vehicles will perform in sort of a system level scale. If we have vehicle I and I-1 here, you can imagine plotting the velocity versus position, where the red vertical line corresponds to our rear end safety. If we're moving faster than the vehicle in front of us, we're going to coast along at a constant speed until this rear end safety constraint becomes active. And then we're going to slow down to form a platoon with the vehicle in front of us. And in fact, that's what our result actually is. If you're ever moving faster than the vehicle in front of you, you are guaranteed to form a platoon with that vehicle as long as it doesn't exit the system on an off ramp or another vehicle doesn't cut in front of you. And so we can actually talk about system level behavior by examining what the individual vehicles are doing. And we've also shown that we can run this in real time in our scaled smart city. So you can see a group of vehicles here. We're releasing them to get sort of a bit of distance and time headway between them. And once they exit this roundabout onto the straight part of the road, they switch over to solving this optimal control problem in real time. You can see the vehicles enter, they sort of travel along with a constant speed. And in this case, we've commanded the leader of the platoon to slow down, because that's going to maximize the chance that all the vehicles behind it form a platoon with it instead of breaking into multiple platoons. And you can see the vehicles slow down until eventually they reach this platoon configuration, at which point we have to actually switch into a platoon maintenance controller. Because of course I haven't said anything about string stability and maintaining the platoon. I've only talked about how we actually reach this formation. But you can imagine then the vehicles switch to maintaining the platoon. Yeah.
Sorry, I have another
No problem.
question. So this, and you talked about, what happens if there's like another car coming in, or there's like one of the
Yeah.
cars just like stops?
Oh, absolutely.
Yeah.
Yeah. So the question is, what if another car comes in, or what if a car stops? So we actually did a simulation with, it was something like 1,800 vehicles with several on-ramps coming onto and out of the system. And it turns out if a vehicle enters in front of you, as long as it's not, if it enters in front of you, as long as its initial state is feasible, so you still satisfy the rear end braking constraint, you just start considering that vehicle as the new one in front of you. And if that vehicle exits, then you just consider the vehicle in front of it instead. So because it's driven by its just measurements of the vehicle around it, you can take vehicles out of the system and add new vehicles in. It'd be a little bit trickier if they stop. So one of the things we considered that I didn't discuss here is if the vehicles have a deadline to reach a certain distance, because you can imagine this sort of trivially becoming everyone's driving at the minimum speed on the highway. And if a vehicle stops, then that's the most drag efficient state that you can be in, right? So you can imagine if the vehicles stop, the vehicles could come down and brake, or if they're going to violate their deadline constraint, they could attempt to overtake the vehicle in front of them. They could relax that constraint until the vehicle's removed off of the road, and then they would accelerate back up to try to maintain their deadline. So there's lots of different things you can do if you sort of add and remove vehicles from the system. Great. So in addition to looking at sort of a one-dimensional problem with ground vehicles, we can also look at two-dimensional aerial vehicles trying to fly in a V formation, as I sort of mentioned in the beginning of the section. So we're going to imagine we have these fixed wing aircraft, maybe like they look like small airplanes. And we've got what we call unicycle dynamics. So you're controlling the speed and you're controlling the yaw angle of the vehicle. And the aerodynamics of an aircraft are much more interesting than a ground vehicle. We have sort of these terms here, C1 velocity squared plus C2 divided by velocity squared. These come from the wing physics. So they've got things like drag coefficients, lift coefficients, and air density built into them. But we also have an additional term down here, and this has to do with the wake interactions of the vehicles. So instead of just creating a low pressure bubble you're trying to move into to reduce drag, we actually get these vortices that spread off of the wingtips, and you get this upward motion of air beyond the wingtips. So you can imagine if this vehicle's in front of me, I want to ride in the upwash because the wind is pushing me up, I'm getting some free lift, and I can spend less energy to fly. And so this is sort of a maybe more interesting problem to look at from a physical perspective, at least. And so this is sort of the second place where this differs from ecologically inspired robotics. because we're no longer just going to minimize the acceleration squared. Instead, we can actually optimize the agent's performance in this system. So you can imagine we could select either the minimum drag speed that we want to match. This is going to maximize the amount of distance we can travel. You can imagine if you're doing some kind of package delivery that may be useful. We can also minimize the power loss to the drag force. This is going to maximize the amount of time that we're allowed to spend in the air if you're doing, say, surveillance and you want to get as much surveying done as possible. And both of these result in quartic polynomials that have a unique optimal speed that either minimizes drag or minimizes power losses. And so what we're going to do here is we're going to minimize our deviation from this optimal speed. So we're actually maximizing agent performance in our optimal control problem. And so we can see this here, where we're minimizing our deviation from this drag force. We're minimizing how much we're rotating in the air, and then we're normalizing it by our constraints. And so if we use this objective function, we can also look at a similar sort of gradient being non-positive type of constraint, because in addition to just our drag force being minimized, we also are going to get some benefit from this upwash in terms of lift. If our upwash force looks like this dashed line, you can imagine if you're a wing behind it, you can integrate along the length of the wing to get sort of a force that's pushing you up. You can also integrate the upwash force times the distance from the center of mass to get sort of a rolling moment that the vehicle has to counteract. And so we can maximize this upward force, and we also want to minimize our rolling moment. And so we can use some sort of trade-off parameter. If we can estimate how much energy we lose increasing our angle of attack versus how much energy we lose by counter-rolling against this rotation, we can construct another function that we want the gradient to be non-increasing. That will essentially drive us up to one of these peaks. And again, I can show you this emergence in our city here. So we're using 5 crazy fly quad rotors. Of course, the physics are not the same on quad rotor drones, so we've had to simulate what these forces look like. But you can see that when we run our controller in real time, this is the Vicon data of the experiment. You get this emergent V shape where the agents are moving into these upwash regions so that they gain some benefit. They're not expending as much energy, and they remain relatively stable here for sort of the short amount of distance we're able to fly them. So to summarize, we've looked at different emergent behaviors that come from minimizing energy consumption. We force the agents into these energy minimizing equilibria, and we get these sort of system-wide energy favorable configurations, either platoons minimizing energy, V formations where we're reducing how much energy or power we're losing. And of course, we also have very useful engineering outcomes. We have a data control method for these multi-agent systems where we're just reacting to the environment and what we measure and sense around us. We have guarantees at the individual level on things like safety, as well as guarantees at the system level, like whether or not platoons are going to form. And finally, it's very easy to interpret why an individual agent may take a particular action. We can look at the finite state machine and say, oh, this is a platoon leader, this is a platoon follower. But you can even look deeper and say, oh, the rear end safety constraint is activated. That's why this vehicle is slowing down. So it's a very nice, easy to understand, sort of robust way to do data-driven control. So for the last part, I've talked about how the agents can sort of react to the environment, but a more interesting problem that we sort of hinted at earlier is what if we want to plan a trajectory over some amount of time? We need to consider constraints. How can we do that quickly enough so that these small agents that we release out in the environment can plan these trajectories and execute them in real time? And the way that we do this is a method called Hamiltonian analysis. We're solving a continuous time optimization problem. We have some initial and final time. We're minimizing this is like our cost that we're integrating over at each state, subject to our nonlinear dynamics and some constraint that we can call G. It may be a function of the state, the control, or both. And in order to solve these problems, we calculate the Hamiltonian, which you can think of as like a dynamic version of Lagrange multipliers. So we have our running cost here, we have our states multiplied by our co-states, and then we have these inequality Lagrange multipliers multiplied by our constraints. And it turns out when we minimize the Hamiltonian, we're able to sometimes recover what the optimal trajectory looks like. We have these optimality conditions we have to satisfy. So we have to minimize our Hamiltonian with respect to control. And we also have these Euler-Lagrange equations that describe the evolution of the costates. We have our dynamics ordinary differential equations, which are another set of nonlinear ordinary differential equations. And so generally, to determine an optimal trajectory, you have to solve this system of ODEs. But if you activate a constraint, such as rear end safety, minimum speed, maximum acceleration, you also get discontinuous jumps in your costates and discontinuous jumps in your Hamiltonian that you have to account for. So in addition to solving these systems of ordinary differential equations, you're also solving these systems of algebraic equations, which also have some added sort of smoothness vectors that require the transitions to obey, sort of enter at like a tangent. And so there's really two big shortcomings if we want to apply this directly to the systems we're working with. The first is we don't have a justification to control acceleration directly. You can imagine controlling the motor torque or the forward force on the vehicle, or if you have an aircraft, maybe you could be controlling the thrust. But so far, we've been doing entirely sort of kinematic control through the acceleration. In addition, the ordinary differential equations are actually numerically unstable. When you combine the states and the costates together into one large ODE, it's very hard to solve numerically. And in fact, sort of the state-of-the-art method for solving this is you start with whatever initial conditions you have. You integrate your dynamics forward using some nominal control input. Maybe you assume you have, linear acceleration or something, and you end up at a set of final conditions, final states. You then integrate your optimality conditions backwards, right? Because you now are sort of decoupling the states and co-states, so you can integrate optimality, and then you check. How far am I away from where I actually have to be for my boundary conditions? And you'll repeat this process until you converge to an optimal trajectory. Now, what I've just described, this is only for unconstrained systems. If you have a constraint, you're additionally going to have jumps in your optimality conditions. You're going to have to switch between unconstrained dynamics and constrained dynamics, and it really becomes a real mess. And so we can address both of these issues by using a property known as differential flatness. The idea is we can take a system such as this differential drive robot, where we're controlling the velocity of the left and right wheel. And if a system is differentially flat, it means we can map these dynamics to a space where everything looks like integrators. So we can control the X and Y acceleration of the robot instead. We can then solve the optimization problem in this flat space and map it back to the original coordinates to recover what our wheel velocities are. And a bunch of different systems are differentially flat. Many robots, even some thermal systems. So it's a very general property of a lot of differential equations that satisfy this.
So, sorry, so what was the requirement for it to be differentially flat?
So sort of the best requirement they have is, does this mapping exist? So you have to sort of exhaustively search and manipulate your equations to see if you can get it to look like integrator dynamics.
But mathematically, how you would describe this?
So
there is a condition, right?
Yeah. Well, yeah.
Not necessarily condition, but there is a.
Yeah. So there's a couple of ways. Like there's a book by Sunil Agrawal, who's
actually used to be.
It used to be at uni. He did a lot of stuff with flatness, and he would say, if you have a system, you can sort of embed it in a higher dimension where you have if you have like two states and like their derivatives, you have like two state variables and two control variables, and then you have your dynamics. You can embed that in like a 5-dimensional space. And then you can cancel out variables and equations to try to end up with these integrator dynamics. It's also related to systems that are feedback linearizable. If you have a dynamically feedback linearizable system, I think you can construct these sort of flat mappings.
Dynamically feedback linearizable systems are differentially flat. Differentially flat systems are not necessarily.
And
before Sunil and others, there was a bunch of French mathematicians that developed differential flatness. But basically, what the answer you're looking for is that you have to find a set of flat outputs
Mhm.
that you differentiate enough times so that they can express explicitly and only in terms of the inputs of your system and the derivatives.
Yeah. So for example, one,
You find the outputs, if you are lucky enough, you differentiate them enough times so that eventually they're expressed as a function of the inputs of the original system and the derivatives, multiple order derivatives.
so,
Essentially, if you can describe your system in this way.
so for example, if you have a drone with 4 propellers, like a quad rotor, you have 4 control variables. And you know that then your differentially flat system is going to have sort of 4 states. And for a drone, you can look at the X, Y, Z position and the yaw angle. And if you take, I think if you derive position all the way down to jerk, and you derive your yaw to be your yaw angle, your rate of yaw rotation, and your angular acceleration, you can write your original system's dynamics entirely into the position through jerk variables and the rotation, 3 rotational variables. But you have to find that mapping in order to say that the system is differentially flat. So that was actually a lot of early results, was just looking at systems and saying, hey, I found a transformation. This is differentially flat. It's.
There isn't a constructive method for defining these flat outputs. That's why Logan was saying that you have to search.
Yeah.
With good intuition, sometimes you find them.
Yeah. Yeah, so like we know a lot of things like robotic arms or like certain rigid bodies, if the forces aren't aligned, like they've just basically tabulated a ton of stuff that's
So it's
different.
mostly like, honestly, a little bit trial and error, right?
Yeah.
You just like look at it and keep searching and searching, and if you find it, great. If
Yeah,
you don't,
exactly. Yeah, it's like stability stuff, right? If you can't find a Lyapunov function, that doesn't mean one doesn't exist. It just means you haven't found it yet, right? So it's the same sort of thing. And so in terms of differential flatness, yeah, it was very popular, I think in like the 90s. This is like the big paper that sort of brought up differential flatness. These French mathematicians talking about jets of infinite order and, you know, all that stuff. And it's sort of evolved since then. And the main application people actually have is they'll convert their system to these flat outputs, and they'll use basis functions, things like finite sums of cosines or splines or line segments. And so they'll have like a handful, they'll have like 100 constants that parameterize this trajectory, and they'll find the best values for those constants to build this piecewise trajectory, and they can pass that back through the mapping to get a approximately optimal control algorithm for their original system dynamics. And the result I'm about to show you, we're doing sort of we're taking what they call the indirect approach, where we're trying to just solve this optimization problem in the output space. And the only result I've been able to find that's similar was published by Chaplace and Petit in 2007 and 2008, some French mathematicians working at Mainz, where they proved for dynamically feedback linearizable systems, such a result should exist. So the contributions here it's a new combination of optimal control and differential flatness. I'm going to show how we can separate the states away from the co-states to remove these numerical instabilities, and how we can create what we call the optimal motion primitive generator, which actually tells you exactly how your system will behave in sort of a rigorous way, and a new numerical approach to actually generate these trajectories fairly quickly. So here's sort of the story of how am I going to find these real-time solutions. We're going to start with our nonlinear dynamics. These don't need to be affine in the control or anything. They just need to have this property of differential flatness. And we have this diffeomorphism, this bijective mapping between our original system states and the set of integrator chains, you know, position and a certain number of velocities. So we can go back and forth between these two sets of variables. Now, what we can do is we can do the same Hamiltonian analysis, but we'll do it in this space where we have integrator dynamics. So again, we have our objective function, we have our constraints, but now our dynamics are integrator, which means it's just position, velocity, acceleration. So we've effectively taken all the nonlinearities out of the dynamics and we've sort of pushed them into the objective function or pushed them into the constraints. And so when we take the partial derivatives of this, all the integrator dynamics are going to become ones and zeros. So we can actually move all the costates to one side of the equation. We can move all the state variables to the other side of the equation. And you can cancel out all the costate variables. And you end up with what we call this motion primitive generator. This is your optimality condition that describes how the systems evolve, and it's numerically stable. So you're able to solve this with, for example, a shooting method instead of that forward-backward type of integration. But in fact, these mu's, these are sort of our Lagrange multipliers, right? They tell us what constraints are influencing the system. So we can systematically go through, and for example, if we set all of the values of mu equal to 0, we know that corresponds to the unconstrained solution. If we set the mu corresponding to our safety constraint equal to 1, we know that this differential equation corresponds to our safety constraint condition where we're on the, up against the vehicle in front of us, or we're on the surface of an obstacle. So you can systematically toggle these mu's to be 0 or non-zero to completely determine all of the different motion primitives that your system can show. And in fact, it's going to be fewer than 2 to the size of mu, because things like having minimum and maximum speed at the same time are kind of nonsensical. So this is the highest number of equations we may have. In reality, we'll have fewer. But then, of course, we have these motion primitives that solve for our trajectory. We can then pass those back through our diffeomorphism, and we can actually generate these motion primitives in our original system space. So if by moving our nonlinearities into the objective and into the constraint variables, we can solve it in the original system instead. But if, for example, our flat variables are the same as our constraints, if our flat variables are position and speed, and our constraint is a speed-dependent safe distance, then the constraint's going to be very easy to solve in this space. So you can sort of pick and choose where you want to solve your optimal motion primitives. And in fact, we can also write the costates explicitly as a function of the state and control variables, because we're able to separate them to both sides. Yeah.
Hold on.
Sure.
I was thinking of saving it, but I'll throw it in there. Go back to the previous slide.
Mhm.
You talked about an objective
Mhm.
for this optimal control problem. What's the objective?
So in this case, the objective function is sort of this function phi. It can be
Psi.
any. Oh, psi. Ah, dang it. I'm sorry. Yeah, so it can be, I think, pretty much any continuous differentiable function. If it ends up being a function of your flat variables, then it won't change. But if it ends up being a function of your original variables that sort of get mapped over, then you're also going to have to map your objective function into the new space. But anything that you're able to write this Hamiltonian out for, so I think it needs to be like all the partial derivatives need to exist with each of the states, and with respect to the control need to exist. That's about as specific as you need to get for this.
I would like to see it in a concrete example, but I'll let you continue.
So I have actually, let me just get through this slide. We have an example coming up in the next one. It's kind of a simple example, but so in this case, we can also write all of our costates in terms of our state and control variables. Again, using the same process of moving the costates to one side and all the states to the other side. And we take this sort of transition we have where we activate a constraint and we get discontinuities in our costates. And let's say, for example, we want to minimize the L2 norm of the control input. We have double integrator dynamics because we're in this flat output space. And we want to remain a fixed distance R away from the origin. There's some obstacle we're trying to avoid. If we plug these into our costate equation, we actually get out some very simple conditions. The control input needs to be continuous. Our velocity in the direction of the obstacle needs to be 0 because we have to remain on its surface. And the jerk in the direction of the surface must be continuous. So we can piece these optimal motion primitives together using these continuity conditions in order to generate trajectories. And so that's exactly what we've done here. We have an agent starting at -2, -2, traveling up to 1, 2. with the final speed left free. So we just know it starts from rest. It ends at this position, and we want to avoid this obstacle centered at the origin. And I've implemented this solution in sort of a naive MATLAB implementation. I solved the system of equations in FMINCON because the system solver can't let you use constraints. And I used ODE 45 to solve when the system is constrained to the surface of this circle. And it turns out, basically the approach is you assume an unconstrained trajectory. If that's infeasible, you assume that the agent is touching the surface of the circle instantaneously. And you can use the point where your trajectory became infeasible as your initial guess for where that point is. If that is infeasible because you aren't able to satisfy your constraints, you then assume that the agent must start here, touch the circle at some point, travel along the circle before exiting. And you can again use the points where your constraints were violated as your initial guess for that. And so running that algorithm, we're actually able to perform significantly faster than iClocks2, but also about 3 times faster than OpenCL, which uses a C++ based Cassidy solver. So this thing's pretty fast compared to FMINCON and ODE 45 and MATLAB. In addition, we're only considering the beginning, the end, and the point that we actually contact the circle. So we only need to know about 3 points in the system. Because these are using basis functions, we actually have to have a uniform grid of about 35 points to get enough resolution to get this similar sort of behavior. I did try the adaptive meshing with iClocks2, but it just continued to adaptively mesh until it eventually threw an error saying there's too many mesh points. So you perhaps could get away with some sort of adaptive meshing, but the state of the art doesn't seem to quite be there yet. And in addition, because we're exactly resolving what happens at this point of contact, we actually get about a 20% improvement in energy consumption. Because instead of just evaluating points near the surface and avoiding it, we're actually just evaluating the point of contact. And of course, it doesn't violate any of the constraints. So to summarize, we've talked about emergence problems. We talked about this idea of solving a medium complexity problem and looking at the behavior of the system as an equilibrium point. We've talked about decentralized control, how we can try to extract guarantees on global behavior from how the local agents are interacting, and also how to drive the system into these energy favorable configurations. We talked about constraint-driven control, how you can have a rigorous data-driven framework where just data that you're receiving changes the boundary of your constraint set. And of course, this is an interpretable method that's guaranteed to be feasible. So you can understand what the system's doing and know that it's going to be able to operate over long periods of time. And then of course, we talked about this idea of fast optimal control, discussed a new approach that's applicable to many different types of problems, anything that's differentially flat. And it outperforms the state of the art, at least for the problem that I've presented here, this obstacle avoidance sort of trajectory generation. Finally, of course, no research is done in a bubble. I'd like to acknowledge all my wonderful lab mates and committee members who are here and supporting me, and also the different funding agencies that have helped make the research possible. And of course, I'd like to acknowledge Mariam and my other wonderful friends at UD who've made everything much more fun. And I've got just a list of the different publications that are my dissertations made up of, and that's some of which I've presented here. And I guess we can take more questions now. Thank you.
Great. So any questions from the audience, either here in person or from Zoom for Logan?
Yeah, and if anyone's on Zoom, you can unmute yourself or type it in the chat.
Any questions for Logan?
It looks like Michael's got one. He's raising his hand.
Go ahead, Michael.
Yep. Hey, Logan. Can you hear me?
Yeah, I can hear you.
Okay. First of all, congrats on the defense. Very good presentation. So I actually had a question about the platooning and just sort of the general construction of the safety parameters. So
yeah.
I don't know if I'm interpreting this right, but yeah, exactly. So when you look at the platooning problem here, you talk about having a safety constraint so that if the first car breaks dramatically, then the car behind it will be able to stop in time.
Yeah.
But I'm just curious if we have like a large system with a whole bunch of vehicles in it, and we assume that probably there's going to be some propagation, reaction time for, any system as the car reacts to the car in front of it. Are we going to get to a point where the car in the back has to either follow like infinitely far behind the other cars, or conversely, the velocity has to be as, infinitely small in order to guarantee that there's zero possibility of collision? It was just an idea I was
that's
about.
it's sort of two questions in one, I guess.
Okay, yeah.
The first is, if you have this disturbance sort of propagating through the system, I guess that's almost more of like a string stability problem, right? If the vehicle in front of me slams on the brakes, how does that propagate through all the vehicles behind me? And that's not something that I actually have considered.
Okay, so we're generally assuming like instantaneous communication here, right?
Yeah. So the idea is we've got a bunch of connected and automated vehicles. They can maybe communicate up and downstream to make better informed decisions about how they're going to move.
Yeah, okay. Mm-hmm.
And sort of once they've formed a platoon, I'm happy, right? I'm like, they formed the platoon, they can switch to some other sort of maintenance controller.
Okay, yeah.
In terms of the following distance needing to be very large, this sort of second term is quadratic in the relative speed, and it's maximized when the vehicle in front of you is moving at its maximum speed, or moving at its minimum speed, and you're moving at your sort of maximum speed. And it doesn't grow arbitrarily large. It's bounded by how fast you can decelerate down to the minimum speed. So
Okay. Mm-hmm.
you have like some vehicles misbehaving and driving very slow. They may eventually sort of slow down the system, but we know the gaps between the vehicles are going to be bounded before the stopping distance doesn't matter anymore.
Yeah, okay. Yeah, and I think the connectivity, assuming there's no propagation time, is probably what allows you to bound that sort of thing too, I would imagine.
Yeah, because you can imagine, maybe having to add some buffer if you have, because you could have a non-connected vehicle in front of you, right? Because you're just sensing data about it.
Yeah.
But worry about like, how much do I expect the vehicle in front of me to brake, or how much are they going to brake? And you can imagine sort of building a bigger and bigger buffer around this set, right? So
yeah.
I haven't looked at the stochastic case for this problem yet.
Mm-hmm. Okay, cool. Thanks, Logan.
Any other questions for the audience here or from the audience in Zoom? Yes, Leda.
So on the line plotting and another one was cluster plotting, right?
Yeah.
So what would define it that like a group of like agents does cluster plotting and the other do the line plotting? Is it based on the dynamics of the system or objectives of the system that behavior?
Yeah, here we've sort of looked at it from like an engineering design perspective. If my objective as a designer is to just maximize sort of the or minimize the energy consumption in the system, that's generally going to fall into like a line flocking type of problem. Whereas if I am as a designer and trying to achieve some sort of objective, like if I want to track a ground target, for example, then that would fall more into a cluster flocking type of problem. But it is a bit fuzzy, right? And like, how different is cluster flocking from like generating a formation? Because there is an objective, but it may, look different. So the boundaries are a little bit fuzzy, but generally, yeah, I've looked at it as like from a system designer's perspective.
Any final questions for the audience? But if that's the case, let's thank our speaker again. So I'd like to ask you guys to excuse ourselves so that we can deliberate here. And also, if the audience in the Zoom, except Rahul, can sign off so that we can maintain. And please stop recording.
Yeah, I'll stop recording. I'm going to need to stop sharing my screen for a second.
Yeah.
I will stop recording.